So let's see what happens. We need to now very carefully define certain terms, right? Certain definitions for delay of various blocks, right? And what we want out of these blocks. So if I have a combinational block, I have an input D and an output Y. Okay, let's assume that my input D changed at this point. Okay, so this is a timing diagram that we should get used to. This switch here, right? This transition means data is switching from one state to another state, but both are deterministic. We know what they are. So this will be data D1, this will be data D2. And the reason I am not drawing it as a binary function is this could be a bus. This also could be a bus, right? So any change in any of the inputs is what we are capturing through this transition here, this transition. So what happens is, after the input changes, the output will start changing at some point first. Now this means this region its data is going through some random transitions. We don't want to pin down what the value is. Okay? Why does this happen? For example, when one input changes, I could have some short path through my combinational block which causes one of the outputs to change, right? But now an other input changes and it may come and overwrite this, right? There is a possibility that you'll have a glitch at one of the outputs, and that glitch is what we are capturing here. The issue is the glitch can affect the circuit going forward. So we have to make sure that the earliest change of data also we should be very careful about. So the earliest time at which data can change is basically called contamination delay. This we did earlier, even for NAND and all that. We said there is a contamination delay, which means the earliest, smallest delay. Largest delay is called propagation delay. So this is, maybe I'll draw this in red. TCD. This arrow mark going from here to here says that it's the transition between D1 and D2 that caused my output Y to start changing. Okay, the reason we need to do this is, later you will see in a flop based system there will be a clock that changes, there are also data that changes, but the output may react only to the clock, not to that data. So by putting this arrow, we are actually saying it is a change in this edge or data here that caused the change in the output Y. This change here is called the propagation delay, PPD. That's the latest change after which the output is guaranteed to be stable. Contamination delay is the earliest time at which the output starts changing, but the data is not guaranteed to be stable after that. Output is stable after propagation delay. Okay, so PCD is contamination delay. PPD is propagation delay. Okay, this is a combinational block. Now we have to see what happens to this is called a flip-flop. The word flip-flop or latch or register can vary from book to book. Rabai has a different definition. We are following what Weston Harris is using. Okay, a flip-flop is a sequential element as defined by what I am going to show you now. Okay, now I have a clock that controls this. dq. Okay. So what am I going to do? I have this clock that's essentially changing like this. Okay. This is clock D and Q. So let's assume by default a flip-flop is always a positive edge triggered flip-flop. Okay, this is positive edge. That means data will be captured on that rising edge of the clock, and data will now then be stable after that. Okay, so let's assume that this data changed like this. So it went from D1, went to D2. Okay, and yeah, so by the way, this one I will call this output here as Y2, means D2 output has now come to Y2, right? This will be Y1. Okay. So let's say that the data changed from D1 to D2 and then it again switched to D3 somewhere in between. Okay. And or I'll make it more interesting. This thing makes a very quick transition. D2, D3 and then D4. Okay. So what should happen? What is the expected behavior of a flop is what we are looking at. I do not know what this output is before, because I do not know what the previous state was. That's what this arrow mark here means. Okay. So now at the positive edge, data that it is going to sample is which one? D2, right? So now again the output can start switching a little early and it can settle finally to some other value. Okay. So therefore there is a contamination delay for the flops as well and a propagation delay, but the origin of these two delays are not the same as that of combinational circuits. I will come to this at a later point. It's not like, because if you look at a flop, there's only one path. There's one, path of inverters or whatever, like, so there's no alternate path to actually cause this contamination delay. I'll tell you where this comes from. Okay, the question is, we are trying to capture the earliest change and the latest change, right? So this will settle to D2. Q will now capture D2, right? On what edge is D2 reacting to? On the, yeah, but what I'm asking is it the change out here or is it the change here? It's with respect to the clock. Therefore, my arrow mark has to start from the clock and come here. Okay. So this is clearly called a clock to Q delay for obvious reasons. Okay. Therefore, I am going to call this TCCQ, TPCQ. Okay, C to Q, the last CQ is basically clock to Q. The first letter C or P is saying it's contamination or propagation delay again. Okay, so what is the behavior now? Now what happens to this change to D3 in between? What will happen? Nothing. It should ignore, right? So this is a very important point. The change even at the negative edge, there should be nothing that goes through, right? So D2 should be captured all through. Okay. Now in order for, so what will happen at the next edge now? It will capture D4, yeah. Again, you will have the similar changes, and this will be D4. Now, in order, like I already told you that there is a sequential overhead, and I said that you can't have the guy placing the brick like this and the other guy taking the brick away. So it has to be placed a little before. How much before? That is called setup time. So in order for D2 to be captured at the positive edge correctly, you have to set this data up, T setup before the clock edge arrives. So this is setup. Okay. Now, after the edge, after the clock edge is done, sampling edge is done, D2 should be stable for some time in order for this to go through, right? This is, this is what we call T hold. The data has to be held after the clock edge so that the data can be captured correctly. Again, the origin of setup and hold time is very different, and we will look at all of that later. Okay. So this is basically, I will just show you that what these definitions are, right? I have them here, right? TPD is logic propagation delay. TCD is logic contamination delay. TPCQ is for a latch or a flop. I'll show you what a latch is. Clock to Q propagation delay. The first P is for propagation. C to Q is the clock to Q. TCCQ again. First C is contamination, clock to Q delay. Okay. And setup and hold time, I just explained to you. Okay. So now we will also look at what a latch based system is. Okay. Latch. So I have a clock. Okay. L. So this is D, this is Q. A flop is edge triggered, a latch is level triggered, right? So in the sense, this is a positive latch by default. What does positive latch mean? It means when the clock is high, data can go through. The latch is transparent in the positive edge, right? And therefore, I have the following. So let's now do the same timing diagram that we did for the flop. Okay, I am going to cause some transitions here. D1, D2, D3, D4. Okay, my clock, D and output Q. So we'll plot the timing now for this. Okay. So as usual, I do not know what this state is, the negative edge. Forget that because we don't know what the previous state was. Okay. What about here? Clock has gone high and therefore D2 should go through, correct? Latch becomes transparent. Okay. And so as usual, you will have some early transitions. This delay is caused by, is triggered by what? By clock or data? Remember, my data changed before the edge. The latch was opaque at that point. Then it became transparent. Therefore, the delay now has to be clock to Q delay, right? So these T, C, C, Q and T, T, sorry? Oh, sorry. Correct. Sorry. Yeah. Q. Now there is a transition from D2 to D3 after the clock has gone high. What should happen to that data? It has to go through. So this is D2, right? This change is now triggered by what? By data, and therefore I will have another term like this, right, which is T. No. The first C or P is always for contamination or propagation. So it is C, D, Q and T, P, D, Q. Okay. Now where is the setup and hold time for the latch? For a positive edge, for a positive latch, what is the sampling edge? Okay, what does sampling mean in terms of transparent and opaque for a flop also? Basically, that sequential element is going opaque at that point. Data cannot go through from input to output. It's going to hold the state. That's what it means. So what is the sampling edge for a positive latch? If it's a positive latch, data can go through when the clock is high. So at what edge does it sample the data? Rising edge, yeah, but you look at the comparison with a flop, right? At what point, when I say sample, it means I'm sampling the data and I'm going to hold it. That means change in data after that should not be able to go through. That's what I mean by sampling. I mean sample and hold. Exactly. So for a positive latch, it's the negative edge which is the sampling and holding edge, right? So I will not put this arrow actually. I will put this arrow here because this is my sampling edge. Okay. So therefore, setup and hold time has to be defined with respect to the negative edge. This is T setup, T hold. Okay. So effectively what happens is at that sampling edge, D3 will get sampled and appear at the output. The change to D4, what should happen there? It will not go through because now the latch is opaque, right? So I will also indicate here the latch is transparent. Latch is opaque. Right? And the change in D4 therefore is lost. And after you come here, now again the latch becomes transparent. D4 is now still held. Therefore, at this edge, you will have a change causing D4 to eventually appear. Okay. So let us look at the logic functionality of this, logic description of this latch. What is it? If clock equal to 1 implies Y should be equal to, Q should be equal to D. Otherwise what should you do? You hold the previous value, or you just leave it. Actually, if you're trying to write this in very long, you can just leave this, right? If I were to implement this in terms of logic gates, where I have if clock equal to 0, then hold Q. Let's say, what is the best logic gate I can use to implement this? Mux, right? A multiplexer. This is a clock. The select line is a clock. If it is 1, then this is 0, this is 1, this is Q. Where should I connect D? Yeah. What should I do on the other end? Simply feed it back like this. Okay. Now, if I want to make a flop out of this, what should I do? If I want to make a flop, so now this is the latch, which means when the clock is high, data can go through. Clock is low, it holds. You have to just cascade two latches, right? This master-slave configuration that you heard of earlier. You cascade two latches, a positive latch or a negative latch and a positive latch together, and you get a positive H trigger flip-flop. Okay, we'll look at that in tomorrow's class.